All right, hello. So my name is Liz, and I'm going to be doing the homework 1 question for transport 2. So I have my tablet here, and I will just go ahead and get started. So the question involves a capillary that is filled with equal volumes of ideal gases A and B on its left and right sides. So let's draw that. So gas A and B. Then it is allowed to mix to equilibrium, and the pressures and temperatures are uniform and constant. So it's gonna mix so that it is uniform throughout. So it's gonna look something kind of like this, except just very, very uniform throughout. But you get the point. So then we want to derive an expression for the relationship between molar and mass diffusive fluxes. And we want certain things in this equation, but we'll get to that. So first I want to talk about the molar flux. So that's usually represented by a capital N, and the total molar flux is equal to the molar flux of component A plus the molar flux of component B in this situation, because there's two gases A and B. And in this situation, since they are mixed equilibrium and they're uniformly and completely mixed, it's going to equal 0 because, say, like when a mole of B moves to the left, a mole of A is going to move to the right. So therefore NA equals negative NB, so the molar flux of A equals the negative molar flux of B. And we can actually say the same thing about molar diffusive flux, which is represented with a capital J. And we'll talk about this later, how the about the molar diffusive flux of A equaling the negative molar diffusive flux of B. This comes in later. And then also something that I wanted to bring up is like that the molar flux of A, if we want to find the relationship between the molar flux of A and the mass flux of A, not capital N, my bad, which is represented by lowercase n, the mass flux, we know that to get from moles to mass, you can just multiply by the molecular weight. So the molar flux of A times the molecular weight of A equals the mass flux of A. And you might think, hey, can't we just do that with molar diffusive flux as well? Well, actually, unfortunately, it's not that simple. And to see this, let's look at the equations for molar diffusive flux and mass diffusive flux. So the equation for molar diffusive flux is molar diffusive flux equals molar concentration times the velocity of A minus the molar average velocity of all the components. So that is molar diffusive flux. Then mass diffusive flux is the mass concentration of A times the velocity of A minus the velocity, the mass average velocity of all of the components. So what is the common term here? Well, it's the velocity of component A. So what we can do is solve for the velocity of component A, and then we can plug it in to this equation. So before doing that, let's look at this term right here. So the molar average velocity is also within another equation that we can look at. So the molar flux which is equal to 0, which we know from up here, equals the molar concentration times the molar average molar velocity. Sorry. So we know that there's a concentration because there's gas in there. So this does not equal 0. So we know something has to equal 0 because the molar flux equals 0. So the average molar velocity is going to equal 0. So that means that this equals 0. So this equation simplifies to this, which then, if we put it in terms of the velocity of A, then that will be the molar diffusive flux of A over the molar concentration of A. And then we can just plug that into this equation, and it'll look like this. And this can also be written like this. And the reason I wrote it like this is because if we look at this term, let's look at it over here. This is the mass of A over the volume, and that's the mass concentration, and then the molar concentration is just moles over volume. So this simplifies to mass over moles, which we know equals the molecular weight of A. This is the mass of A over the moles of A. So we can plug that in for this term. And that is what we get. Scroll down here a little bit. So let's go back to the actual problem first. So the question is asking that we find the relationship between molar and mass diffusive fluxes in terms of the molecular weights of the gases and the mass fraction of A. So right now we still have this velocity term. So we want to look at the equation for that and see if we can simplify it further and get to the mass fraction and just the molecular weights of the gases. So the equation for the mass average velocity of all of the components is going to be the mass concentration of A times the velocity of A plus the mass concentration of B times the velocity of B over the total mass concentration. And that makes a lot of sense because we're just breaking it down into its components. And so next we are going to look at hold on, give me a second. Oh, yes, I remember. So next, we're going to look at how we can take this equation and do it in terms of the B component. So we can then plug this in to this equation. So you can just do the velocity of A equals the molar diffusive flux of A over the molar concentration of A. You could do the same exact thing for component B, which we derived earlier. So let's just go ahead and plug that in. So rho A times J A over CA, whoops, sorry, plus rho B JB over CB all over rho. And then we can do the exact same thing for rho A over CA. Let me highlight this. So rho A over CA and rho B over CB. We can do that equaling the molecular weight of A and B. So we can use that we did before, and it'll simplify to, here, I'll scroll down a little bit more, simplify to the molecular weight of A times the molar diffusive flux of A plus the molecular weight of B times the molar diffusive flux of B, which the molar diffusive flux of B, I'll write it over here, equals negative the molar diffusive flux of A, because like we were saying before, in this situation, it's when it reaches equilibrium, it's going to be uniformly dispersed and completely flow throughout evenly components A and B in the capillary. So when 1 mole moves from from the right to the left, the mole of the other component will move from the left to the right, like I explained earlier. So that's why the molar diffusive flux of B equals the negative molar diffusive flux of A. So I'm actually going to, instead of putting JB here, I'm going to do negative JA. So I'm going to do it like this. So now we have the velocity term simplified down. So let's go ahead and plug it into our mass diffusive flux equation so right here. So that's, actually, let's use this one. MAJA minus rho A. And then we're going to plug in the whole V velocity equation. All right, so now just a couple final steps here. Let's look at this rho A over rho term. So we know that rho A over rho, sorry, I should say the mass concentration of A over the total mass concentration is the mass of A over the total volume over the total mass over the total volume. So that is actually equal to mass of A over total mass, which equals the mass fraction, which is what we need for answering this question. So let's plug in mass fraction, WA, in for rho A over rho, the mass concentration of A over the mass concentration. And then I'm also going to pull out the JA, the molar diffusive flux term, just to polish it up. So it's going to look like J. Yeah. All right. So this is the answer for the relationship. Whoops. There we go. For the relationship between mass diffusive flux of A and molar diffusive flux of A in terms of the molecular weights of A and B and the mass fraction of A. So that is the answer to the question. Thank you.